I'm currently a scientist at the Pacific National Lab. I mainly work on geothermal and carbon storage projects. But currently, I'm talking about research I did when I was a PhD student working with dogs to make dogs happy, I guess. And I think Dr. Feng has already set a good stage of the nonlinearity research. Here is a basic recap. When I mention nonlinearity, I mainly refer to nonlinearity in the rock mechanical behaviors. And the stress strain behaviors characterize the rock deformation under an external disturbance. Studying the rock mechanical properties is very important for many geophysical applications. For example, when we are drilling a wellbore in the oil and gas production, we need to ensure the wellbore stability after disturbance. And also for the seismic wave propagations, we need the wave velocity models, and the wave velocity depends on the rock mechanical properties. And there are common two assumptions, or kind of like very simple assumptions, which is the rock is elastic, and also the rock is linear elastic. And in current research, we just put a question mark into the second assumption, which is the rock has long been observed that is nonlinear elastic. And here is, I just show you a very long paper that is conducted 100 years ago to show that the compressibility changes with the pressure. We could see that if the rock is linear elastic, then the compressibility should be a linear line, independent of the pressure. However, we could see that compressibility is highest when in the lower pressure, and then it levels off. And similarly, for the velocities under the confining pressure, when we are sending pulses through the rock samples, it's also pressure dependent, and we could see that the time decreases with higher pressure. And all these evidence shows that the rock is nonlinear elastic, and we cannot use simple linear elastic models to model them. And in our study, we use the third-order elastic model trying to calculate the nonlinearity of the rock. And the main essential part of the TOE model, which is the energy conservation, that the energy is all stored in by the external deformation, and it can be calculated using the scalar string energy density function, and it's path dependent. And here is, I think, the essential constitutive equation for the third-order elastic model. It basically shows how the stress is related to the strain by the stiffness matrices. And you can also think about as the Taylor series expansion. Originally, if we only look at the first term here, it's basically the generalized Hooke's law. And in order to calculate nonlinearities, we add the quadratic terms of that. And if we assume the rock is isotropic, then the second order terms originally had 21 terms were reduced to only two unique parameters, lambda and mu, which is the Lambda constant we know, and another this third order elastic matrix were reduced to only three terms, which is the ABC, but it's not the same ABC as Dr. Feng showed, which is the ABC for the stiffness matrix in the third order terms. And our goal here is, of course, to derive the protocols so we can use to measure and to find how to measure these moduli and also measure them. And I need to mention that I think in the literature, it's exclusively using the dynamic isotopic method to measure the third order terms by using the wave velocity versus stress. And in our cases, we use the static method by finding these nonlinear elastic parameters using the stress and strain, because we already long know the difference between the dynamic moduli and the static moduli. And in our application, for example, we want to know the geomechanical applications. We think the static moduli is of course more applicable in these sections. And here is the original equation, the general equation that I showed you previously. And in order to do the testing in the lab, we need to make the test specific constitutive equations. So in the lab, we could commonly do the compressive loadings, for example, the hydrostatic triaxial test or the uniaxial test, and there is no shear introduced. So if we're assuming that we can do this in the lab, then these equations have been derived for the test-specific constitutive equations that we are squeezing the rock compressively, no shear is introduced. And here is kind of a little bit complicated equations, but we can simply think as the left term, which is the stress, and then all the string combination terms, which is the string combinations, and we can measure the stress and strain in the lab, and the only thing left for us unknown, which is this 5 elastic moduli we want to study and to measure. And it's similarly for the stress in another kind of y direction and z direction. And because the string terms here is kind of very complicated, we can simply simplify them using the Greek letters. And then from this equation, you could clearly see that we can form the system into a linear system equation, and then using the least squared invert for the parameters we are interested in. And after I presented the test-specific equation that I derived, then first I think I want to do, which is of course validate the analytical solutions using the numerical method. So in the finite element model, I just choose a very simple kind of geometry, which is a cube, and I apply the same displacement boundary condition to this cube. So which is kind of mimics the rock is under the hydrostatic compression. And this parameter is coming from the literature, but I want to mention that all these parameters is measured dynamically. And then we could see how, and then I just record what the stress look like in the middle of this cube. We could see the figures here, which is the stress versus the strain, and the solid and the dashed line, which is the enclosed solutions and also numerical output. And we could see that the analytical and numerical output fits which is kind of like overlap with each other pretty well. It makes just that our analytical solution that we derived correctly calculates the nonlinear stress response under the hydrostatic compressions. And also I do the similar validations for the triaxial and also uniaxial test. Then after we get the theory, and after the theory is validated, then we can move toward in the lab how we can measure it in the lab, trying to get the elastic properties. And here, which is just a summary and a recap of the previous problem, which is we have the constant equations relating the stress and strain, and which is a test specific. So in the lab, I could set the hydrostatic and uniaxial test and combine the constant equation, which is 2, 4, and 5, and then get them together and to invert for the nonlinear parameters we are interested in. Here is a simple uniaxial experiment set up to show you how we did it in the lab. First, for the rocks, we apply the 2 axial and 2 lateral strain gauges to measure the strain, and for the stress, it's measured by the load cell underneath it. And in the lab, we first do the pre-stabilized small cyclic loads to stabilize the sample. And then in the formal test, we do the loading and unloading test. And we also tested for different loading rate to see the loading rate effects. And also we repeated for multiple cycles to ensure that we have the repeatability of our result. And the next setup, which is the hydrostatic experimental setup, in this case, we sealed the sample with epoxy, so the oil won't get into the rock, so there's no core pressure. And then we just using the manual pump to increase and decrease the pressure and the strain, which is measured by the data acquisition system. In this test, we also use the similar features, increase loading the pressure and unloading. And for each increment of the pressure, for each increment change of the pressure, we try to hold it for 10 minutes for the pressure stabilization and thermal equilibrium. And I want to mention that we do not have the temperature measurement, so we just have a guess that it will be equilibrated for the thermal effects. And then we could see a few results for that. The first, which is the result for the wave Fontainebleau sandstone. Here is the stress and strain curve for the hydrostatic measurement. And the different colors here show the strain at different measured at different strain gauges we have. And we could see, first of all, we could see that all the strain gauges will all overlap with each other, meaning that suggesting the rock is more isotropic. And then we could see that actually, in this case, we cannot distinguish the loading and unloading passes. So it will suggest that the rock is not hysteresis involved, and then this is path independent. And then we can see the result for the uniaxial test. And this curve shows the the uniaxial strain, and this curve shows the lateral strain. And we could see that even though we use a different loading rate, but all the curves are overlapping each other, it's meaning that there is minimal loading rate effect. And then we also repeated 3 cycles, and our result is repeatable. And for this kind of rock, we only see a weakly nonlinear stressing curve. And here is SEM image shows the quartz packing. Then we have show the result for the frag from the blue sandstone. And similarly, here is a result under the hydrostatic settings. And for this kind of rock, we could clearly see the hysteresis for the loading and unloading cycles. So this rock is path dependent. And then for the uniaxial test, we could see that even in the uniaxial test, we could see a large hysteresis loop in this rock sample. And this rock is nonlinear, it of course is apparent nonlinear stressing curve. And we think the reason for this rock being path dependent is because this intergranular pores that have the opening and closing of the cracks. And after we measure stress and strain in the lab, we could do the inversion at the scheme as I presented. So we can invert for these 5 elastic parameters. And then in order to test the feasibility of the T model for this rock, I can plug these inverted parameters back into the considered equations, so we can get the predicted stress and also compare it with the lab measured stress. And we could see that for the wave from the blue sandstone, it can characterize this rock pretty well. However, we could see that actually this scheme or the theory model fails very miserably for this kind of rock. And we think that the reason for the infeasibility of the theory model for that is because the rock is actually path dependent, as I showed you for the large hysteresis loop, and which violates the assumption of the sub-elastic model. And secondly, we also think that because this rock may undergo the large strain we can see there is order of magnitude difference between these 2 rocks. And because we do the Tiller's expansion, so it should be limited into the small strain. And after we get this elastic moduli, we want to see how it will actually change the subsurface response in one applications. So we just want to study the application to see how the rock properties will affect the wellbore stability. So we have 2 cases. First case, which is a linear elastic case, and the second case, which is the third-order elastic case, where we have these 5 elastic moduli. And similarly, I also set up some numeric models in FEM, and then I have the cylindrical well presented in the cube, and the cube is under the normal Fortin regime. And now we will see how the stress will changes along this pink path. Here is the figure showing how the stress around this pink path with respect to the angle in the circumference. And the dashed line, which is numerical nonlinear case, the solid line, which is the analytical linear case, and the marker, which is the numerical linear case. And first of all, we could see that the linear case, we could validate the linear case with the Cauchy equation, so we can see the overlapping between the marker and the solid line. And then we can focus our attention to the dashed line. We could see that the hoop stress will amplify when the rock is nonlinear. In addition to this 1D comparisons, we also draw a cross section around the perpendicular to the axis of the wellbore, and we could see that the stress between the linear and nonlinear cases indeed will differ, and then the difference will disappear away in the far field. After we get the stress field, we of course can do to see how the rock will fail, and we could see that when the rock is nonlinear, it will have a bigger breakout region. And this difference in the wellbore failure patterns will, of course, impact the analysis of the wellbore stability and the quantitative constraints of the stress magnitude, since we need to observe these failure patterns in the field and then try to invert back. I think this is my last slide. Sorry for the high speed. I only have 1 minute left. And then first that in order to calculate the rock nonlinearity, we use the third-order elastic model, and it requires we calculate these 5 elastic parameters. And then secondly, we derive the test specific density equations, so we can measure these elastic moduli through the simple compressive test. And then thirdly, the feasibility of the Turing model depends on the path independency and the small string. And lastly, even though we make many simplified assumptions by assuming the rock is linear elastic in many applications, but I think we should call attention for the rock being nonlinear elastic, and it will be a very important parameter input for many applications to study the subsurface response. And here we show a simple application to see how it will differ in the wellbore stability analysis, and it will, in our current cases, it will result in a larger wellbore failures. Yeah, I will leave my slide here, and I'm open for any questions or comments if you have any. Technology and